So today I'll be talking about some algorithms for a very general problem, that of estimating the trace of a matrix. And I'll talk about some applications such as evaluating partition functions. This will be based on some results from these two papers with various collaborators. But more generally, I'll try to talk about some basic ideas that go into these algorithms and try to place our results in that context and show precisely how we achieve the kind of improvements we do. So firstly, well, this problem of trace estimation, why are we interested in this? So just to recall, the trace of a matrix is the sum of its diagonal elements. If the matrix is diagonalizable, it's also the sum of its eigenvalues. Now, from physics, there are a lot of applications. Given a Hamiltonian, either quantum or classical, you may want to compute something called its partition function, which is the trace of this exponential minus beta h. This is a useful quantity, for instance, in thermodynamics or statistical physics. Other applications include computing things such as this spectral form factor, which people studying chaos, quantum chaos in many body systems are interested in computing. So there are other related problems, basically regarding about understanding the spectrum of a matrix, such as computing the spectral density, which is counting number of eigenvalues of Hamiltonian matrix in a certain interval. And a related problem, something called the low-lying spectral density, which is the same problem, except you want to know how many eigenvalues are near, say, the zero or the lowest eigenvalue. That's useful for problems in so-called topological data analysis. Another application involves computing these things called these Shatton p-norms, which again have various applications in quantum information, linear algebra, etc. So the whole point is that this is a fairly general problem for which there are lots of applications in fields we are all here quite interested in. So we want to think of maybe we want to think of good algorithms for this problem. So a bit more precisely, the problem setup is we have some large size matrix A. And for the quantum algorithms, we will consider the setting where this matrix is implicitly specified. That is, if you want to write down the matrix, which is exponentially sized, it's going to take a lot of time, and we don't want that. So we might want something like a small specification. In the quantum case, it often makes sense to think of this matrix given as a sum of unitaries, where each of these unitaries can be implemented by some small size quantum circuit, or say specified by some products of Pauli matrices. You can also think of more general access models such as sparse matrices, but I won't talk much about that. Then our task is to estimate, say, the trace of the matrix A, or certain polynomials of a trace of A raised to some power P, or more generally, some function of A. And again, as I showed in the previous slide, these have various applications. There are two kinds of error goals you can ask of this problem. So X here is like the trace you want, and X hat is the estimate. Firstly, it could be an additive error goal, which is this thing must be smaller than some number epsilon. The second is like a relative error goal, where the precision you demand must also be some factor of the true quantity. So second one is typically a stricter demand. I'll talk about both of these problems. I'll start with the first one, which is an easier problem first. So the results I'll touch upon at various points in this talk will be an algorithm which uses certain limited quantum resources to estimate the trace or a partition function. Then I'll talk about what you can do if you have a fully coherent quantum algorithm. And in particular, we give some techniques that reduces the space requirements of such algorithms. Lastly, I'll talk about a classical algorithm which uses quantum information theoretic techniques to improve running time over a previously known state-of-the-art classical algorithm. Now, in the last case, we're actually dealing with some explicitly specified matrix, which and exponential-time algorithms. But just to clarify that in the classical case, we won't think of this implicit specification. So I mentioned this setting about limited quantum resources. So what does that mean? Well, we consider this very restricted quantum model where you have a bunch of noisy qubits, n of them. And in fact, these are in the maximally mixed state. So this is the density matrix I over 2 raised to n. So there's no coherence at all in these qubits. And then at the top, you have a single qubit, which has coherence. It's a clean qubit. And the canonical thing you do in this kind of setup is that you apply a Hadamard to the clean qubit. Then you do a controlled unitary, the control being on this clean qubit. And then you do measurements, single qubit measurements on this lone clean qubit. Okay. And that's all we are allowed to do in this kind of setup. And this is inspired by basically information processing in nuclear magnetic resonance, which was like a prototype of quantum information processors from a while back. And there, the molecules are in an almost thermalized state, And you can describe the kind of behavior you get there by this kind of a model. So that's kind of the early motivation why people thought about this. So why is this model interesting? What can you do with it? So one thing is that, suppose I do this measurement in the Pauli X spaces, you can convince yourself by some few steps of linear algebra that the probability of getting, say, a 0 on measuring this in the X spaces, okay, that's related to the real part of the trace of the unitary. In particular, if you could estimate the probability of getting 0, you could estimate this trace of u over 2 raised to n and the real part of it. Likewise, if you could measure sigma y here instead, a similar probability would give you the imaginary part. So now you can do repeated measurements, collect measurement statistics, and actually estimate by using some kind of Chernoff bound kind of thing, how many measurements you need to estimate this trace to some precision. And you can show that you can estimate trace of u up to a normalization of 2 raised to n with an epsilon additive precision by using O of 1 over epsilon square measurements. And this is equivalent to what people call the short noise limit in quantum metrology. And why would this be an interesting? Well, people have defined a complexity class called DQC1 based on what you can do with this one clean qubit model. And there you can formulate some kind of decision problem. And then they have shown that this problem of estimating the trace of a unitary up to this normalization within some inverse polynomial additive error is in fact complete for this complexity class. So the class is kind of defined as you do a polynomial size circuit, you do this measurement, and you ask whether the measurement probability is greater than 2/3 or less than 1/3, something like that. And that defines like a decision problem. So this trace estimation is a complete problem. And furthermore, if someone tells you to estimate this normalized trace, it turns out there is no polynomial time classical algorithm. At least we don't know of one yet. So this indicates that even this very limited quantum model does something which we don't know how to do classically. So maybe there's a quantum advantage here. And people have found applications of estimating this trace of normalized unitaries, including evaluating certain things called Jones polynomials, which have applications in quantum field theories, also knot theory. I won't talk much about that. But just to give you an idea of like further evidence for hardness in this kind of computational setup, people have also shown that there is quantum advantage in topological data analysis based on evidence from DQC1 hardness results. Also, further evidence is that there is a paper showing that if you want to think about sampling problems, where you're sampling from some output distribution of DQC1 type circuits, that can also be classically hard. So that's just to give you some idea that this model does something that is beyond classical algorithms. Now, the problem I want to think about is, of course, this trace estimation. And I talked about how to estimate traces of unitaries. Well, what about more general operators? To go there, I will think of basically a block encoding. So here, A is some matrix whose trace we want to estimate. And we're given some block encoding of it, which means that I have a unitary W, which acts on like m plus m prime qubits. And if I take a partial inner product, this gives me A over A up to some normalization. So this 0 tends 0 O times m prime is like a flag state marking which subspace your A is in. So this is something called a unitary block encoding. So given this, I want to estimate trace of A. And this kind of gadget lets me do that, and not just traces of unitaries. And the idea is simple, is that I introduce m prime more additional qubits and do C naughts pairwise between these m prime qubits that were there in the block encoding and the ones that I introduced. So you can show, again, quite easily that if I now think of this larger unitary U comprising these C naughts and the W, the trace of U will in fact be the trace of this particular block encoding. And this, one way to see this is that consider that some of these states were in the, like this m prime qubits were in the one state. Well, that would flip the qubit over here. And therefore, this won't contribute to the trace because here you have effectively identity acting on these qubits. That's like one way to see it. But the main line is this, we can also do traces of block encodings in this kind of setup. And if I want to think about, well, what is the complexity of getting this trace? Well, it's almost the same. I have this 2 raised to 2m, where m with number of qubits A act on, and then 1 over epsilon square, which is like akin to the short noise limit. But I also gain some overhead because I have this more qubits floating around now and this normalization. So if your block encoding is not prohibitively expensive, all this is fine. But I just wanted to mention this because if you want to do a careful analysis, these are things you need to take into account. I won't worry about that. I'll mostly be concerned about this dominant scaling, which is the dimension over epsilon square kind of thing. So given this gadget to do a block encoding, this now gives us a general technique to estimate traces of matrix functions. So we have heard from several talks in this conference that these techniques such as qubitization, quantum signal processing, quantum singular value transforms, this can effectively encode block encoding of matrix functions. So given some block encoding, unitary block encoding of a matrix H, so this entire matrix is unitary, and in particular subblock, it contains H. I can use QSVT, quantum signal value transformation, to get a approximately unitary, which encodes f of H in some particular block. And then there's some garbage here, but the main idea is, again, I can project out this block, use the gadget in the previous slide, and get a trace of the function of H. I can also do something simpler, which uses this sort of LCU idea, linear combination unitaries idea, which was a precursor to this quantum signal processing, which is I can approximate matrix functions using, say, a linear combination unitary operators. In particular, I can think of like a Fourier series approximation, and then use so-called Hamiltonian simulation to basically get an approximation to this f of H. So this function of f of H now is approximately a linear combination of Hamiltonian evolutions for different times. So these are unitaries. Now, if I think of trace of f of H, this is like a linear combination of trace of different Hamiltonian evolutions. So this is the kind of idea that we used in one of our papers to give an algorithm for estimating the partition function. So I'll briefly outline that now in the next slide, just to show you a concrete example. Now, we won't think about a Fourier series approximation. I'll instead do a Chebyshev approximation. So I have this e power minus beta h, whose trace is the partition function. And I can do a series expansion of this form. So these ik of betas are coefficients, which are Bessel functions, and these tk of h are like Chebyshev polynomials of the Hamiltonian. And I can truncate this series efficiently and all that, so that can be done. Now, again, using qubitization, given the block encoding of this Hamiltonian up to some normalization, I can generate Chebyshev polynomials in this Hamiltonian. So then I can just plug in my block encoding over here, get the trace, and effectively, this gives me a general way, it gives me an algorithm to estimate the partition function. But again, you can take this idea and use it for other matrix functions as well. So you might want to ask, well, what is then unknown about estimating traces of general functions of matrices in this model? So it turns out there's a result predating ours, which is due to Kate and Monteraro, who classified what are the functions whose traces you can estimate in this model. So they're considering the problem of estimating trace of f of h over 2 raised to n, the normalized trace up to some inverse polynomial error. And they show that if the function satisfies some certain smoothness conditions, you can always have a TPC1 algorithm. So this is kind of a precursor to the technique I outlined in the previous two slides, because they use effectively quantum phase estimation. I won't explain how, but the problem is if you use quantum phase estimation, etc., you get a worse scaling with precision. Whereas if you use these newer block encoding ideas, you can get a better scaling. Now, it might be interesting to just do a full analysis of what you can do in this with this newer block encoding framework of general function trace estimation. But so that might be an interesting direction to pursue. So going back to like the basics, what have we learned from all this? We have learned that we can estimate trace of an exponential size matrix and various functions of it, given certain access model of it, with roughly 2 raised to 2n over epsilon square uses of a quantum circuit acting on just one clean qubit and a bunch of noisy ones. All right. So we have the scaling over here. And the immediate follow-up question one might ask, well, okay, so we know this from this noisy quantum circuit. What can we do if we allowed like a fully coherent quantum computer? So just have all n clean qubits. So you can do something better, which is use quantum amplitude estimation. So this is a pretty standard idea, and I'll just outline how it's done over the next slide, because this will lead into effectively our next result. So our goal is to estimate this trace by an amplitude estimation, which is a standard algorithm in quantum computation, which is given some unitary and a particular amplitude, something of like I, in an input of I, U, F of this form. You have an algorithm which can estimate this amplitude using 1 over epsilon uses of the unitary. Now, to use this in this kind of trace estimation, I need to write the trace as an amplitude. And the trace on the left-hand side here, it's not an amplitude, it's a sum of a bunch of amplitudes, if you can put it that way. Now, what I can do is I can go to a larger space, also called church of larger Hilbert space, and do something like this. So I have I tensor U. I have two copies of this, whatever system I had. And then I sandwich it between this sort of bipartite maximally entangled state. So U acts on this one set of one register, and on the other, I have nothing. And then I have this bipartite entangled state. And I can prepare this efficiently with a quantum circuit that uses just Hadamard's and C-naughts. All right. So what this says is I can now run quantum amplitude estimation on this larger unitary and evaluate the trace as an inner product of this form. So since I'm using quantum amplitude estimation, my scaling immediately improves to 2 raised to n over epsilon. So the main takeaway from this slide is I got a quadratic improvement over here. In the one-clean-qubit model, you had 2 raised to 2n over epsilon square. And this I could do because I'm writing this trace as an amplitude by sort of purifying it and going to a larger dimensional Hilbert space. And because of this, I needed n more qubits. So this is for a unitary, but pretty easily the same thing carries out to when you have a unitary block encoding of a matrix A. So given an A, you can again think of writing the trace of A in a similar form by doing this purification and doing this kind of replica of the system. Now, this thing on the right-hand side is not yet an amplitude, but using the fact that this A is encoded in a block encoding, you can also write it as an amplitude. And this, I won't explain this, I won't spend too much time here, but you can verify for yourself that this works out, that you can estimate the trace of a block encoding and encode it into some quantum amplitude, and therefore use quantum amplitude estimation. The key thing that I want you to take away from here is that this trick of purification, it introduces an extra n qubits. And this is what we will concern ourselves with over the next few slides. I'll show you a technique where we can reduce this n to some extent. All right. So here we had n qubits on the system, some flat qubits, and we needed an extra n qubits. And I'll tell you how to reduce this n to something smaller. For that, I will need a technique which we call Clifford compression. So I'll define something called a Clifford projector, which is I have this operator in the bracket here, which is the projector onto the all zero state of some n minus k qubits times identity acting on the other k qubits. And then I apply a unitary, which is something called random element of an n Clifford group. So the Clifford group is quite important quantum information. A Clifford circuit in general is something you can generate using just C-naughts, Hadamards, and phase gates. Okay. And if you choose such a circuit uniformly at random, which you can do efficiently, you can implement such a Clifford projector. All right. Now, the key fact what they want to use is that this Clifford group is like a finite countable subset of the unitary group. So if I average over this Clifford projector, I get something proportional to the identity up to some normalization factor. All right. And this follows from the fact that the Clifford group forms a so-called one design, and it reproduces the first moment of the Haar measure over the unitary group. That's like the technical reason. That's what we're exploiting here. And this is what we're using. So then we define a Clifford estimator, which is this trace of not just A, it is we apply this projector, PU, for a randomly chosen Clifford unitary, and then consider trace of this matrix. So you might wonder, okay, what are we gaining from this? Well, it turns out because of this key fact here, that this estimator is an unbiased estimator of the trace we want, which is this 2 raised to minus n times trace of A, the normalized trace. And now I can think of expanding this trace of PU of A. So this PU of A has this projector hanging around. Now the trace converts outer products to inner products. So recall from the previous slide, I had the trace as a sum of amplitudes, and I needed to purify that to go to a larger Hilbert space. Here, I have a sum of fewer amplitudes effectively, because I'm using this projector, which kind of fixes some of the qubits into this pure state already. So what that means is that I need to only think about purifying this k number of amplitudes. So I can only add k number of additional qubits. And that's really the main point. We need to purify over a k qubit subspace. So we just need k additional qubits instead of n. And this we do by using this Clifford projector. Now, the key question, of course, of here is, well, how big does this k have to be in order for this to be a good estimate? So for this, we'll use the fact that the Clifford group is also something called a 2 design. So and this we can use to compute the second moment of this estimator I defined in the previous slide. Why do we want to do this? Well, let's just bound the variance of this estimator in terms something like this. There's some factors depending on k and n and the trace of a. Now, using standard inequalities such as like Chebyshev inequality, you can ensure that if you choose your k to be something that scales with log 1 over epsilon, for any randomly chosen Clifford unitary u, this ZU of A will be an epsilon precise estimate of the normalized trace with high probability. So that's it. Just choose one random Clifford and then choose your K large enough and you're done. And then estimate this, and this gives you an estimate of the trace. So the key point is you need only O log 1 over epsilon additional qubits for purification. And this helps you reduce how many more qubits you needed. Now, this is just, I should clarify, this is just the number of qubits you need to purify. You will need some additional qubits to do amplitude estimation on top. But following this paper, you can show that this is, again, a constant number. Now, we want to apply this to, in particular, to the partition function. And again, you can use these block encoding ideas I talked about, which is you come up with a block encoding of e power minus beta h and use all of these gadgets I introduced, the purification trick, the Clifford compressed purification trick. And you can show that the algorithm you get by following this kind of outline, it has running time 1 over epsilon times 2 raised to n over z. So in this slide here, I'm asking for a relative error estimate, which again you can do by using the result from Aronson and Roll. And I'm hiding away a bunch of factors. So here you see the scaling with 1 over z. And this 1 over z is because I'm asking for a relative error estimate. Now, just in comparison, I talked about this algorithm in this one-clean-qubit model. This would have a running time that's roughly quadratically worse, again, hiding away a bunch of factors. And one thing I want to mention is that to show that this DQC1, this one-clean-qubit algorithm can give you a relative error estimation, we have to invent some general classical techniques for relative error estimates, which can be of probably independent interest. So if you're interested, please ask me about that later. So this is just to contrast these two quantum algorithms. And again, having this fully coherent quantum setup gives you an overall roughly quadratic or polynomial advantage. So now I want to get to the final part of the talk. So we saw basically the quantum part of quantum algorithms for doing this kind of trace estimation. Now I'll briefly talk about a classical algorithm for this same problem. And I'll show that how using these Clifford compression idea, you can essentially speed up this classical algorithm for trace estimation. So I'll try to explain this very briefly. So in this setup, you're considering the trace of a positive semi-definite real matrix A. And the strategy, the general strategy of this algorithm, due to Hutchinson and then improved by these authors, is to estimate this trace by computing like a whole bunch of inner products. In a bit more detail, you choose 2m random vectors whose entries are random variables taking values plus minus 1. And you think of this projector Q onto the subspace spanned by roughly these m of these vectors, so half of them, and A applied to it. And then they built an estimator for the trace, which is trace of Q over A, plus again a sum of various inner products. And now you can think of doing some kind of Gram-Schmidt orthogonalization of the subspace spanned by these vectors. And you can write the first term in this estimator as also a sum of inner products. And in particular, it was shown that for m equals 1 over epsilon, this HA is a relative error estimate to within precision epsilon of the trace of A. So this is Hutch plus, as was called in this paper by Meyer et al. And the key point what we want to improve upon is that this involves evaluating a bunch of inner products. And what we effectively do is show that you can get away by evaluating fewer inner products by using the same Clifford compression idea. So we design a compressed matrix, A hat of size 2 raised to k times 2 raised to k. And it's defined in the following fashion. So an element of A hat, x, y, where x, y are vectors with entries 0 or 1. So each of x and y are 2 raised to k sized vectors. This is defined from the original matrix A by thinking of having a vector x, pairing it with a bunch of zeros. So basically you have a 2 raised to n size vector, fix n minus k of those to be the 0 elements, and then let x be randomly 0 or 1. Same with y. So again, then you apply this U dagger, where U is your random Clifford operator from the previous slide. Now, by the same arguments that I mentioned earlier, what you can show is that the trace of this compressed matrix is related to the Clifford estimator, which in turn was a pretty good estimate of the trace of the original matrix. And that's really this line of argument. You've taken this Clifford estimator and expressed it as the trace of a compressed matrix. And then you apply the Hutch++ algorithm, which evaluates a bunch of inner products to this compressed matrix. And this in particular requires you to do fewer inner products. That's like the rough sketch of the argument over here. What benefits do you get? Well, the running time of the older Hutch++ algorithm was scaled as TO A over epsilon plus 2 raised to n over epsilon square, where this TA is this cost of basically doing matrix vector multiplications for this matrix A. If you do this Clifford compression, you lose this 2 raised to n over epsilon square scaling. So you get TA of TA plus 2 raised to n plus some logarithmic corrections over epsilon. So this is an improvement in the regimes where you're not demanding, say, exponentially high precision. Because if you demand exponentially high precision, there's this 1 over epsilon over 4 factor floating around here, which can become dominant if you demand really ridiculous precision. But for anything like inverse polynomial n precision, this is an improvement. So this brings me basically to the end of the classical algorithm. So just to summarize, what did I talk about today? Well, I introduced this one-clean-qubit model and showed you that you can get polynomial time algorithms to estimate normalized trace of unitary operators. And you can generalize this to get trace of block encodings, matrix functions, etc. And I talked about an example applying this to partition functions. And then I showed that if you allow yourself more coherent quantum qubits, so not just restrict yourself to having a bunch of noisy ones, you can do better by using amplitude estimation. And that led to this next result where we could, so amplitude estimation, if you recall, required us to purify this n-qubit trace. And then by using this two design property of the Clifford group, we could reduce basically the number of qubits you need for this purification. And finally, I briefly outlined that if you use this Clifford compression in a clever manner, it can also speed up a classical algorithm. So just in terms of outlook, here are some things you can perhaps one could think about, is that there was this difference in scaling, this quadratic difference in the one-clean-qubit algorithm and the fully quantum algorithm. So for like something like an intermediate number of clean qubits, could one get some intermediate scaling on the precision? Is that something people might be interested in? That might be something to investigate. The other thing is, well, this TQC1 model was inspired by NMR, but this is maybe not very practical for NISQ era, where you don't have a bunch of noisy qubits just to start with. What happens is, well, your qubits decohere over time and become noisy. So can one define maybe an analogous model for NISQ era devices and try to think of some complexity class? Maybe people could think about shallow quantum circuits. Maybe there's been work already done. So if you know some, I'd be happy to learn about them. And more generally, in terms of techniques, we use this Clifford compression idea. And this was also used for giving like compressed descriptions of certain quantum states in the paper by Gossett and Smolin I highlighted earlier. So I'd be interested to know if there are more applications of this technique. And the last point is perhaps more speculative. So in this talk, I talked about this very general setup where you're given a matrix, which may be unitary, maybe not unitary, maybe it's some matrix function, and you want to estimate traces of it. And you can, but there's this normalization factors, all those things that come in. So at some point, it feels like you're trying to shoehorn into quantum certain problems that don't quite fit in. But there are also these other problems, which this Jones polynomial thing I alluded to, certain BQP complete problems also related to trace estimation. BQP also DQC1 complete problems, which involve evaluating complex partition functions. Now, those are not directly relevant because they're perhaps somewhat unphysical, but the techniques that are used there are more quantum. So basically, like going by something Jordanis Keranidis said yesterday, maybe one could think of things inspired more by, well, what can you do efficiently in quantum setups, rather than trying to go for applications at the outset. So that's more a remark than an open question, perhaps. So, but those are the things that might be interesting to think about. So with that, I'll thank my collaborators, so Yeet and Rolando collaborated on this work on evaluating the partition functions in one-clean-qubit. And then with David, Sergey, and Pavel, we gave like a more of like a complexity and efficient algorithms and exponential time algorithms for partition function. And I talked about some parts of this second work today. So with that, I'll end my talk and thank you all.